Okay. Now the next chart just start give you a heads up about our flow solver, Leo. All right? And this what I'm spelling out is to give you, you know, I will not go into detail how we solve the equations, but to give you some idea what do we do, right? So code Leo is a computational fluid dynamic code that gives both accurate and fast solutions for following reason. Okay, some of the reason or some of the capability. First, the capability is, as I said, cover from very low speed to transonic speed of 3.5 Mach number. Right now, only working for ideal gas. As I said, also it can do both steady and unsteady. Okay. Make it more very flexible to cover a lot of problems you're interested in. The code can do both structured mesh and unstructured mesh and do it efficiently using advanced convergence technologies. We also make it a multi-block so that you can stack many cases together to run on serially or break them all out to run parallel. And the numerical procedure we use to solve the fundamental fluid dynamic equation, that is the time average Navier-Stokes equations, is as follows. We use cell vertex approximations for the fundamental conservation laws, such as continuity equation, conserved mass, stream momentum equations is Newton's second law, conserve a momentum. This fifth equation will solve the conservation of energies. So we solve 5 equations. In addition, we add 2 more equations to solve. If you talk about turbulence flow, that's the free kinetic energies and omega. We're using Wilcox 98 model of 2-equation turbulence modeling. And this numerical procedure itself, the cell vertex base, was proven more accurate with given mesh than the central difference scheme. We're also using something called distribution formula to assure the proper propagation of convection or acoustic waves without relying on the fourth order smoothing to achieve wave propagation. So it's more physics-based procedures. That allowed us, the distribution formula allowed us to use very low numerical smoothing. What's the advantage? Why we need smoothing? First question. Because we saw solve the conservation equations. Numerical smoothing required is to make sure the oscillation associated with the shock can be damped out. Conservation law tell you far state, but locally, once you have something in between, the equation is not balanced because the state in between supersonic and subsonic is not sonic. There's 2 states, but generally you do calculation give you 3 state. That 3 state will introduce oscillation. That oscillation you have to be damped by second order smoothing. This is something you cannot avoid. You either use upwind scheme or using the numerical second order smoothing. They are really achieve the same purpose. Then the second, we use fourth order smoothing. The only reason we use fourth order smoothing is not to make the solution stable. It's try to, to touch it up because we do this using this distribution formula or convergent acceleration multi-grid. When you start using interpolation scheme, which is now physics-based, you introduce error. One way to take away this error is using smoothing. The smoothing, we only add a very low fourth order smoothing to take away the unnecessary or even decouple, only associated with the interpolation associated with multi-grid. Okay? So overall, the numerical procedure is second order accurate in space and time, regardless the type of mesh you have. Okay? The off-center difference schemes that generally you have to have regular mesh, then it's second ordered. Once you have highly skewed mesh with a changing size, quickly, then you're no longer second order accurate in time. Okay. And so that's really talking about numerical scheme itself. Then there's a convergent acceleration. We use pretty common practice, local time step. And during preconditioning, it's gauge pressure, so assure us to go to very low Mach number with accuracy. On top of it, we have two convergent acceleration procedure. One is for multi-block structure mesh, another used for the n-structural mesh. Okay. Last one, as I mentioned before, we can do time-accurate simulation. Time-accurate simulation is more efficient if you're solving for Navier-Stokes equation with the wall integration. You need using something called dual time step. Each iteration you try to make the solution reach a local steady state imbalance. That's called dual time stepping. Okay, so all right, the last one I think I'll talk to you a little bit about on the code is can do both Cartesian coordinates and cylindrical coordinates. Cartesian coordinates generally, daily application for instance, if you're interested in do a race car, you use Cartesian mesh, unless your race car is so large and 1/4 of the Earth, probably now you're using cylindrical coordinates, right? But if you're really a tiny car on a flat surface, yeah, using Cartesian coordinates. However, on the other hand, cylindrical coordinates has a tremendous advantage if you're working with the rotating machines. So we do both of them. All right.